We had some work yesterday on exponents. And how did it go? Okay, how do I interpret those sounds? Is there a question and any problem you'd like to discuss? Are there things that we need to look at, or are we okay?
No. Could you look at a couple of them for me?
Would you like to look at?
I have 33 and 35 and 43.
33, 35, and 43?
Yeah, just because
Okay, let's
I'm
see
very
what we
unsure when to do what. Plus,
okay,
minus.
when to do what? That sounds like the title of a good book. When to do what?
We're confused enough not to know how to ask the question we need to ask.
We just have clever statements, right? Okay, 33. We have 5 over 5 to the minus 1. And typically, you'll see a phrase simplify, something of that nature. So I'll just leave that there. It's sort of, it's not going to work well. Let me see if I can pile some materials on there to flatten it a bit. Not much, but let's try writing that up on the screen in a moment if I can get some chalk. And what we'll do is write 5 over 5 to the minus 1. This is number 33. Okay, Ernie. Now, what is understood as we look at the board is we have 5 to the first in the numerator. Now, this gets back to, you do have choices, and I guess one of the things I would suspect, whether it's in a 70 class, later on when you see this again in 90, it's the indecision of what to do, and you have several choices, and so, well, how do I start it? And you, instead of just jumping in and trying something, you sit there undecided for a few minutes. The first comment is you could argue that anything that's with a negative exponent in a denominator can be brought to the numerator with a positive exponent. So you could argue that that'll just be 5 to the first times 5 to the first, which then is your 5 to the second, and you'd have it. So as far as a solution, we could argue that. Another approach that's a little less mechanical that says, okay, why can you bring this up to the numerator as 5 to the first, is to understand that this is another way of interpreting what you were originally given. Because the 5 to the minus 1 says you're taking the reciprocal of 5 to the first. Well, if that's the case, then you can either mentally invert and multiply, or you can say this is equivalent to this expression. Because that complex fraction, that compound fraction, does imply a division. Now, if I'm going to divide by 1 over 5 to the first, I know I invert and multiply. So I now know that I would have 5 to the first, okay. We will stop and see what we've got going. Good morning, Jim Curl. Is the what now? Well, let me ask Ernie. Ernie, I have a call from Amy asking if simulcast was switched on.
Yeah.
Okay, Ernie's saying simulcast is switched on, but you aren't getting it at home. Just a dark screen. Is there any way, Ernie, that you can call anybody and see if we can get things going here? Ernie's going to try to make a call and see. We had this problem yesterday, and the district seems to be doing some things with the server that may be affecting this, but we're going to try to follow up. So don't panic, and the alternative, if it doesn't come on momentarily, is to watch it in the library, or I'll have it as an encoded version. So Ernie's trying to find out now.
Off campus, Dr.
Off campus, Amy? Yeah, at home, off campus. Okay, so what's your feedback, Ernie?
Bill's going to check it out.
Bill's going to check it out, so maybe it'll work, and if it does, just give me a call back so I know. Thank you, Amy. Bye. Okay. This then is 5 to the first, and then we would do what? Add the exponents, and we would get back to here. Now, those are two very different solutions. You could just look at this and say, well, I'm dividing by, therefore immediately go to this without the x in between. So there is no one way of seeing it, but somehow or the other you have to find a way you're comfortable. Perhaps this is the best one, just sort of like an elevator. If you're going up a floor or down a floor, you can switch the sign. Now, the thing I don't like about that, somebody's going to say, well, I was just told switching the sign when I go up or down, and with no sense of it, and then I haven't prepared you well. So there's one thing mechanically of doing something, and then do you understand it? Huh?
I did it, I just, because the bases were the same, I just did 5 to the first minus -1.
Ah, another approach.
So it's not
Okay,
wrong.
that's one I didn't think in terms of that, but yes, the bases are the same, so you're going to subtract the exponents. And I feel like, why didn't I think of that? You're right. That's even better. I like that. That's the fast track. Okay, 3 approaches. I was thinking of trying to, what does it mean to do that, but just by subtracting exponents because the bases are the same. Okay, I would go with this third one as the best yet. One way to do it? No. Best way? I can't even argue that. Best way in some ways, I see this and immediately think, okay, I'll put it up here as 5 to the first, and I'm there. But if you just subtract exponents, you're there just as fast. All 3 work. Does that answer anything for you? I hope.
Yeah, it does. It makes it easier.
Okay, and there isn't a one way. I think the bottom line, do you understand what you've done and why you've done it, rather than just becoming mechanical? And then at some point, and this gets back thinking, Terry, to our comments about how you do something until it grooves in, and it's mechanical, but it's mechanical based on doing the right things. You practice a process here that is based on either knowing you're taking a reciprocal or you're subtracting exponents because the bases are the same, and after a while you just do it and don't even think about it.
There's a caveat to that, though. Practice doesn't make perfect, it makes permanent.
Ooh.
So if you're practicing the
Yes.
right thing.
Boy, does that... Okay, we've been talking about guitar playing a lot before class started. And the old adage, cliche, practice makes perfect, you hope. And if you don't practice it the way it should be done, you just make permanent the error that takes forever to get rid of. And sometimes never, it seems. And point well taken. That is indeed the case. And what we're hoping that as you practice it, what conceptually, mentally, is occurring here in the algebra is an understanding that goes with it. Otherwise, you make permanent a process that's going to lead to further difficulties. So it's a rather interesting dilemma. You said 35 also, correct?
Yeah, but I'm looking at 35 and it looks like it makes sense to me. I was having a bad day yesterday and I think
That's my whole problem.
35. Well, let's just see what...
like it makes
Okay,
sense to me
now,
now.
if we look at it with the wisdom we have gained from 33, now, would it make sense to... I'm thinking of Pam's statement now. Just go ahead and subtract exponent 12 minus a minus 3, you're there. Or to think of it as my first approach, the x to the minus 3 goes the top as x to the third. Now you're adding, and you get 15 for your exponent. Or to say x to the 12th divided by 1 over x to the third, invert and multiply, now you're x to the 15th. All of it after you do 33 suddenly maybe makes more sense. Now the next one you said was 43?
43.
43 is over here. Now, the question only makes sense if you're asked to write with positive exponents.
Yes, you are.
Now, if you are requested to do positive exponents, I hope when you see q to the minus 8, in your head is 1 over q to the 8th. So now you have p to the 5th over q to the 8th, and you're done. Is there necessary that we write that on the board? I'm getting no shakes, head shakes that say no. Okay. Any further question on any of the problems? Okay, Laura?
Can you do number 69? Because it was kind of difficult.
6-9. Okay, that's the mess. Let me bring this down just a little bit tighter. I
wanna
keep
see
wanting
it.
this to bend, and it's giving me resistance. Okay, there's my, and we'll leave that up there, Ernie, long enough for me to write it on the board. So I have, in parentheses, x to the minus 1, y to the second. I'm going to put z to the first, even though it's not there, and a minus 2. Then in the denominator, another parentheses, and I have x to the minus 3, y to the third, z to the first, to the negative 1. Okay. Now the question. Is there a best way? I think no matter how you see this, getting this negative 2 brought in directly probably makes more sense. But you could, if you wanted, simply bring what's in the top to the bottom and the bottom to the top with positive exponents. The thing I don't like about that, it is so easy to miswrite an exponent from where the original problem is. So I'm going to, as a choice, bring this minus 2 straight across. So I have x to the second, y to the minus 4, z to the minus 2. And in the denominator, I then have x to the third, y to the minus 3, z to the minus 1. Now that step allows you two choices here. My own tendency is just look for common bases and subtract exponents. But I know in the past I've had students who said, well, I'd rather rewrite that. They would rather take this y to the minus 4, drop it down here immediately to a y to the fourth, bring the y to the minus 3 up to the y to the third, and so on down the line, getting rid of every single negative exponent in the problem because negative exponents bugged them. You could do that. Or, again, my own inclination is to do this, changing as few things as I can to minimize the opportunity for making some careless error in the process. But again, it's a choice. Now the thing that's diabolical about this is suddenly you're looking at what? Negative, 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 negative. You've got more negative signs doing it this way. And if you have trouble with subtracting a negative number, then you can avoid that difficulty. So as it stands right now, this becomes, looking at what I had here, what I'm going up here, you have an x to the minus 1. Of course, that can't stay. I think you're supposed to have it with what, ultimately? Positive exponents. But for the moment, that's x to the minus 1. Y to the negative 4 plus 3, which is negative 1. Z to the negative 1 plus 1, which is z to the negative 1. And understand that that in essence is x, y, z to the negative 1, which is 1 over x, y, z. Could you do it differently? You bet you could. You could have right at this point said, I don't know where I'm going to write that. Okay, just a moment. Okay, Ernie, we have a little more space over here. Let's just slide over just a little bit. Thank you. And I'll try to back off here so we can see it. I'll rotate. I'm going to take this and rewrite it with positive exponents, totally. That's another approach. So I have x to the second. This y to the minus 3 I'm bringing up on top is y to the third. The z to the minus 1 I bring to the top is z to the first. I have an x to the third, a y to the fourth, and a z to the second. Now what I've done is take this and rewrite it so anything that was in a denominator with a negative exponent floats, and anything that was in the numerator with a negative exponent sinks. And as we float and sink, we change the signs. That doesn't explain anything about why it works. It just gives you a technique. But now I note that x squared over x cubed gives me 1 over x. Y cubed over y to the fourth gives me 1 over y. Z to the first over z to the second gives me 1 over z, and I'm immediately to 1 over x, y, z, and I didn't have to really subtract exponents. Where would I like you to be, looking at what you have to contend with in general, and the answer is here, where I'm pointing. The ability to take and subtract negative exponents and understand what you can do. Now, what we'll do, Ernie, is slide now as we come over to here. You get to this point. Now, you could have said that's 1 over x times 1 over y times 1 over z, which is this immediately. At least 3 different ways that we can approach it, and my guess is there are wrinkles that could give you another 1 or 2 beyond the 3 I've addressed. If you just want to answer the question, quit giving me choices, tell me what to do. And that sometimes is the lament. Then the first step down to here, immediately to here, would be my recommendation. If you don't want choices, then play by the rules. Exponent outside the parentheses, bring it in. But where you have to be careful, you have to put this z to the first each time, or it's so easy to forget to bring that minus 2 in with the z. Yes?
When up at the x negative 1,
Up here?
yeah.
Okay.
When you're going to bring that down and make the xyz positive, what I wanted to do was not have that 1 there.
This one?
Yeah, just xyz.
But you would have to, from the standpoint, this means 1 over x, this means 1 over y, this means 1 over z, and if you're going to multiply those together, wouldn't you get 1 in the numerator and an xyz in the denominator and end up with this answer? I mean, it may be nice to say, I don't want a 1 on the top because it's on the top right now and I don't want to put it in the bottom, but you have to.
So if it was all positive xyz at the top, then it would just be xyz.
Correct. Then if we had x to the first, y to the first, z to the first, that is xyz.
Okay.
But the minute you see those negative exponents, think reciprocal. Any other question there?
Can you do 71?
71. Let's see where that is. Okay, as we slide across to 71. Okay, Ernie, to the document cam. Okay, this is a slight variation on what we had before. Now, it's a little bit easier in some respects because you don't have 2 separate parts to the fraction you're dealing with. I'm not articulating that as well as I'd like. Let me write the problem and I'll try to express it as we look at the problem. So we have, let's see, xy to the minus 2 in the numerator, and I have x squared y in the denominator, and I have it all to the what? Negative 3. Okay. Question as we look at the problem now, right? You could simplify inside first. Does that make sense? Simplify inside first. So if I did that, I'd still want to write this as x to the first and a y to the first. So my one approach I could take, that is x to the 1 minus 2 y, that, let's see the problem again, Ernie. I just realized I did something silly. That is y to the minus 2 and not a z. Okay, back to the problem. I have a minus 2 minus 1, and that's still all to the negative 3. So this is x to the minus 1, y to the minus 3, all to the minus 3. That is x to the third, y to the ninth. Are we in agreement with the final answer? You may not agree with the method, but do we agree with the final answer, x to the third, y to the ninth? I'm seeing a few heads nod. What's another approach I could have done? I could have looked at this immediately and said that's x to the minus 3, y to the 6th over x to the minus 6, y to the minus 3. Then this comes down, I'll rotate again, x to the minus 3 minus a minus 6. Oh, and I didn't leave room. Okay, how are you going to do that, Curl? Times. I'm going to set this down here just so we can see it. Y to the 6 minus a minus 3. Now note, this is going to give you x to the minus 3 plus 6, which is 3, and y to the 6 plus 3, which is 9. And I'm getting the same answer, but with a different approach. Out of curiosity, how many of you did this technique? Okay, how many of you did this technique first? Nobody did that one first. Okay, that accounts for half of you. What else did we do? Ah, so what you set up here, okay, alternative, flip first. Is that what I'm hearing? So you say this is x to the second, y to the first, over x to the first, y to the minus 2, all to the third. Okay, clever. How many did that? One of you. Okay. That's x to the sixth, y to the third, x to the third, y to the minus 6. That'd be a nice way of doing it. That gets rid of a negative sign. Okay, what else did we try? Nothing else? So the rest of the other half didn't do it. Okay.
Looked in the back of the book.
That could get you an answer. But you didn't suffer enough. You played the CD, and that was your presentation. Okay, any other comments on 71? Okay, let's fold the paper and pass it in, and I'll get a chance to see what fun you had. Okay, let's tighten in that shot, if you would, Ernie, please. Okay. Division of polynomials is next. Here is the subtitle for this section as soon as I get to that subtitle. And see if I can get the camera to... There we go. Let's try it, Ernie. Division of polynomials. Now, the question, of course, what does division of polynomials mean? Well, the first comment. Okay. You need to remember how to do long division with regular numbers. Decimals. Long division with integers. For example, if I ask you to divide 12 into 1728 without a calculator, that long division process, I hope you remember. The other thing to remember is that a fraction means division. Now, one of the first comments when we divide a polynomial into a polynomial is the simplest version would be a monomial into a polynomial. So if I had x squared plus 3x all divided by x, write down x squared plus 3x. So you have x squared and then plus 3x. So you have two terms. Now to say divided by x means you draw a line underneath the x squared plus 3x and put an x underneath. Is that making any sense? I'm going to go to the sideboard, and the kind of problem we're talking about, let's see if I can get everything here. Okay, let's cut to the document cam. This is the type of problem we're talking about, and it's similar to what I just got, x squared plus 3x. Mine was a little less elegant, perhaps, than what's on the document cam, but if we cut from the document cam to the sideboard, you see the same problem, same type of problem. And so the question is, what do you do here? There is a temptation to cancel, and there's a little statement that's given at the top of what was on the document cam as we go back, where it says for you to understand that if you have in general a plus b over c, we break it into two parts. This is the reverse process of what you typically have done when you've added fractions. That is, we're saying this is rewritten as a over c plus b over c. If we started at the bottom and went to the top, that's the argument you get for adding with common denominators. This is reverse process. So the argument is the x squared plus 3x over x can be rewritten as x squared over x plus 3x over x, and to understand that the x is canceled into both parts. So this becomes simply x plus 3. The danger is to sit there and cancel only part way. And so this is a very dangerous process to think as a shortcut. You cancel the x here and get a wrong answer. Break things into pieces is probably the best argument there. So that's the first level of what we would call division by a single monomial. Another one of a similar nature is to say, let's go back to the document cam and take that problem as it's written. The point being, if I simply had 12x squared, and I'm going to change it now, over 6. Now that's not the problem written. But if I had this, do you understand the potential dilemma of dividing 6 here and 6 here and screwing it up? You have to think of it as 12x squared over 6 plus 6 over 6 to avoid the trap. This then becomes 2x squared plus 1. Now what's another way of doing that? Well, I'm going to do something that I ask you to think of in terms of yesterday and the day before, that numerator could be thought of as what? 6 times the quantity, 2x squared plus 1. Now we're going to refer to that as factoring, but now note the 6's would then cancel, and you'd be left with what we have down here. Now I'm going to make a statement that goes with this. Basically, you cancel factors, not terms. You're canceling factors, not terms. So when I cancel here, or reduce, I'm reducing 2 factors. If I were to sit up here and say the 6 and the 6 I'm going to cancel, I'd be canceling terms. So again, as a little phrase, cancel factors, not terms. Very important statement that can be made. Now I'm going to rewrite this in a slightly different way, because this lends itself to long division as you learned it, where you would say 6 into 12x squared is 2x squared. Then you do what? You multiply the 2x squared times 6, get 12x squared, subtract and get 0, bring down the 6. The 6 goes into 6 once. We had a plus sign there. 1 times 6 is 6. You subtract and get 0. Now that's a long division kind of process that we can carry through. Now I again have given you 3 different ways of seeing this problem. One is to think of writing this numerator in a factored form and then canceling the factors to get this down here. Another is to take the original problem and write it into the sum of 2 fractions with the appropriate denominator and then simplifying that. This is a long division algorithm that is not all that different from what we do if we take 12 into the 1728, where I'm saying the 12 into the 17 goes once, I subtract, I get the 5, and you bring down the next digit and proceed. It's the same process that I'm illustrating here. Now the difference, when I bring this 4 up here, I don't what? Typically put a plus sign between it. Now if you want to play the game technically in a correct way, to say 12 into 1700 something, this is actually 100 we're getting here. So I could say that's 100 plus now, and then this 4 is really a 40, so I'd have 100 plus 40 and then plus 4, and now it starts looking like this. But we let place value take care of itself, and of course as I finish this problem out, reminding you of the process, we can carry out a complete algorithm here, and the place value takes care of itself. Okay, now the question, what happens if we have a little more complicated problem? And what I'm going to do now is fabricate a problem based on a trinomial. Do you recognize that trinomial? What kind of trinomial is it?
Where perfect square.
perfect square. Okay. But nevertheless, I'm going to consider this quotient. Now that's an implied division. That says divide 2x plus 1 into 4x squared plus 4x plus 1. So what I'm going to do is treat it in exactly the same way I did this division here, but instead of dividing by a 6, I'm dividing by a what? A binomial. So I'll put my 2x plus 1 out in front. I'm going to put under the division sign or symbol here the trinomial. Now please note, I have everything in descending order. I have degree 2, degree 1, degree 0, degree 1, degree 0. So I step down in the way that we think of writing a polynomial. We can still see up here without changing, 6 went into this 12x squared. So I'm going to play the same game. 2x goes into 4x squared, 2x. So I put the 2x above the 4x squared. Now, I took the 2x squared I had up here and multiplied by the 6, just like I took the 1 and multiplied it by the 12. So the process is exactly the same. 2x times the 2x gives me 4x squared, but then what I do? Multiply the 2x times the 1, which is plus 2x, and then I'm going to subtract. Now, if we're subtracting 12 from 17, you do it in your head and you get a 5. If I subtract 12x squared from 12x squared, you just say, hey, I get 0. Well, I'm going to ask you to understand that when we subtract, we said that you change the signs and add. So I'm going to put in parentheses here the sign changes I'm making, rather than crossing through the plus and making a minus. Make sure you show yourself the sign change you've made. So this is going to go to a 0 here, and the 4x minus the 2x is going to go to a positive 2x, and then I do what? Bring down the 1. Are we okay in that step? Then the 2x, I now ask, how many times will it go into 2x? And it goes 1 time, so I put plus 1 up here. 1 times the 2x is 2x. 1 times the 1 is plus 1. Then I'm going to show the change of signs, because I want to subtract. And I get a 0 here plus 0, no remainder. And so my argument is, my answer is 2x plus 1. Now how would you check a problem like this, or any division problem? You would say multiply the divisor times your quotient. Well, 2x plus 1 times 2x plus 1 indeed is what? 4x squared plus 4x plus 1. And it checks. And that's why I asked you at the beginning, do you recognize this as a trinomial perfect square? If you did, note the alternative you could have argued. You could have said, that was the numerator, and here's what I had in the denominator, and then what?
Good cancel.
You could have immediately said, cancel, and I have 2x plus 1. That's the kind of thing that we will do much more of later. But right now, we're just asking you to learn this long division process. Okay. Yes?
I don't understand why you subtracted the 2x.
Okay, let's come back. Well, we're going to slide over, Ernie, to what I had here with the long division, because the algorithm that we use here is exactly what I'm going to use here. When I did the 12 into the 1728, I got my 1. I said 1 times 12 is 12. And then what did I do? I subtracted, correct? So in essence, I changed the positive 12 to a minus 12 and add. And I did that in each step, correct? So I'm subtracting each time to get the remainder, what we call a partial remainder, to continue the algorithm. So if I look at what I did here, when I got the 4x squared, I say subtract this answer from what we had here. Well, another way of looking at that is change its sign and add. Does that answer the question? Where is it still? Where now?
On the 2x.
Here?
Yeah.
But I'm subtracting this whole thing, correct? Whatever I get here, I subtract from up here. And I got the 2x from 2x times 1 is 2x. Otherwise, this 2x times that binomial gave me this binomial, which is an answer now, and I'm supposed to subtract that from what I had before. In the same way, if I come down here and say, well, I had a 48 here. Well, that's 40 plus 8, and this is 50 plus 2. So I could have said, take the 40 from the 50. Well, that gives me 10, which I'll add to the 2, giving me 12, and 8 from 12 is 4. Now is it? Okay. Okay. What happens if I try this same idea, and I'm going to again rig a problem for you, but I'm trying to illustrate some things we have to be careful about. This time I'm going to take 2x minus 1 into 4x squared minus 1. So very similar. But now it's going to be, and I'm going to get myself out of room here so fast it's not funny. But I'll do what we have here. What do you recognize in the top? I understand this is an implied division, but what do you recognize in the top of that fraction? It is a difference of 2 squares, which will then be written as a product of a sum and a difference. 4x squared is 2x quantity squared. 1 is 1 squared. So what you're really seeing there is 2x plus 1 times 2x minus 1. We know the answer is going to be 2x plus 1 when we get done. Okay, again. The argument is that this numerator is simply 2x plus 1 times 2x minus 1. How do I know that? Because this is the difference of 2 squares. I have 2x quantity squared. I have 1 squared. So if this is the case, what could I then do? Cancel and be left with 2x plus 1. So I know what the answer is going to be. But let's do it now with the long division. I guess if I wanted to be consistent, and I should try this, I'm going to do this as 2x plus 1. You can slide over just enough, Ernie, I can pick up this too. See, I had 4x squared plus 4x plus 1 over 2x plus 1. So I'm not making so many things different. I'll keep the same 2x plus 1. But all I'm doing is now, in the numerator, 4x squared minus 1. So I'd be canceling the 2x plus 1. Now here's the wrinkle. Plus 0x. I'm creating a placeholder, like a column. So the algorithm, if you don't see a power of x, has to have the missing power of x with a coefficient of 0. So I had an x to the second. I was missing an x to the first. So I need a placeholder for that column, which I'm going to call 0x to the first minus 1. Now you'll see why I need that in the next step. 2x goes into 4x squared.
Twice. 2x times.
Okay, 2x, right? I'm going to get me a little more room there. I have 2x here. Not 2, but 2x. Then, 2x times 2x is 4x squared. But notice when I take the 2x times 1, I'm going to need a place for that. That's why I added the new column with the placeholder of 0. Are we okay there?
Mm-hmm.
Now, coming back to Jennifer's question, I like putting those minus signs that I've changed. So I'm going to add, and now the 0, but this becomes what? Negative 2x. And then what must I do?
Here, bring down the negative 1.
Bring down the negative 1. Are we okay there? Now the 2x into negative 2x.
Negative 1.
Negative 1, agreed? And then that negative 1 does what? Multiplies times the 2x plus 1, giving me minus 2x. Then the minus 1 times the 1, negative 1. I'm going to subtract, but the simplest way to keep from getting messed up here is change your signs and add, and I get the 0 and a 0, and I'm done. And I have for my answer 2x minus 1, which is exactly what we would have obtained had I canceled these two factors that are the same. And I'm wanting you to see that as an entity, as a factor, that I'd be canceling a factor, not terms. So we need a new bumper sticker. Cancel factors, not terms. Any question there? Okay. New problem. Oh boy, am I going to make this one work here? I'm going to take, in the denominator, x squared plus 2x plus 1. So now I have a three-termed divisor. This is following in that same principle that you probably remember with some less than happy feelings doing long division as a kid, where you did 3-digit divisors into 7-digit numbers and you thought it was unfair. Okay, I understand that. Let's see what we can do here. Let's do x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1. Tell me what I just did to create that problem. I did not just make a mess.
Pascal's triangle.
Pascal's triangle, I took what is the numerator? It's x plus 1 to what power? The 4th, because you have an x to the 4th, right? So that's x plus 1 to the 4th. What is the denominator?
Oh.
X plus 1 to the 2nd. So if this is really x plus 1 to the 4th over x plus 1 to the 2nd, then what is my answer going to be?
X plus 1
Plus 1 to the
second.
2nd, which we know is x squared plus 2x plus 1, so we know what the answer is going to be. So it's nice when you rig the problem.
How?
Okay? We know what we're going to get and why. Maybe. Okay, so what am I going to write out here? X squared plus 2x plus 1 into x to the 4th plus 4x to the 3rd plus 6x to the 2nd plus 4x plus 1. So I created a problem based on what we were doing the last couple days. This is about as bad as they get. There's still another wrinkle I've got to show you, but this one will carry through. So you would say what? X squared into x to the 4th is x to the 2nd. Agreed? So we put the x to the 2nd there. And then you get to just do what we did, which is x to the 2nd times x to the 2nd, which is x to the 4th, plus what?
2x cubed.
2x to the 3rd, agreed? Okay, so 2x to the 3rd plus x squared, agreed? Then next step. Change the signs, and I like, again, to put that little parentheses, and then we'll add, and the x to the 4ths are gone. What do I have for the next? 2x cubed, agreed? 4x cubed added to negative 2x cubed. So that's a 2x cubed. 6x squared minus an x squared.
5x squared.
5x squared with a plus sign. Still okay?
Mm-hmm.
Then what? Bring down the next term. Now we usually think of bringing down the next digit. Well, these terms are like digits. I sometimes put a little arrow there if I'm wanting to help guide what should be done next. Then what happens? Your first term, x squared, into the first term of this partial remainder. So I have x squared into 2x cubed, and it goes 2x. Agreed? 2x cubed divided by x squared becomes just plus 2x. And that's nice because that's what we wanted. Remember what our answer was supposed to be? Okay. I'm getting looks that I can't read again.
Can you say that again?
Yeah.
I'm getting looks I cannot read.
No.
Back that whole
Back that whole thing up.
Rewind.
Okay, rewind. This was my remainder when I subtracted.
Got
Yeah.
that.
So I'm going to go back to my divisor, and then what? Take the first part of that into the first part of this. Do you agree that that's 2x? To say that I'm taking x squared into 2x cubed means I'm taking 2x cubed over x squared. The x squared and the x cubed leave you an x, hence 2x.
Okay.
Ask if you aren't following. Okay. So I'm going to take this 2x and do what with it? Again, multiply by all the terms in the divisor. So that's 2x times x squared, which is 2x cubed. If things are working, what always has to happen here? This first part better disappear. It did, or will. It shall. Then 2x times 2x is 4x squared. 2x times 1?
2x.
2x. Remember that old yell in high school, give him the x, the x, the x?
No.
It was give him the axe, the axe, the axe. Grumble. Change the signs. Now what? This went to 0. That's good. That's what I want. Okay, what about this? 5x squared, and I'm adding negative 4x squared. That is
X squared.
x squared. A plus sign.
Or 1x.
Then I have 4x added negative 2x, which is
2x.
2x. And then I still have what?
1.
Plus 1. Do you see that my remainder is exactly my divisor? So this whole thing would go into this whole thing 1. And 1 times that by the, what property?
Identity.
Identity, good, is going to be x squared plus 2x plus 1. Change the signs. They are the same. So by the inverse property, we get the identity for addition, which is 0, and I'm done. Did I get the answer I should? Yes. Let's do a different problem.
You have no room.
Okay, where are we going to write a new problem? Okay, Ernie, we're going to go all the way back to the front of this. I have a little bit of room over there. I see a little bit of space that I didn't use. Okay, so we're going to pan together. Right here, there is space. Here's my new problem. Let's see, I'll create a new page. A new area. Okay, my problem I want to consider. X to the 4th. Just a minute, I've got to think this one through. well, this isn't going to work as well as I may have in mind. Minus 2x squared plus 1 divided by, meaning there's over, x squared minus 1. Now, do you know what, in fact, yeah, we'll do that. Do you know what the answer is?
X squared minus 1.
X squared minus 1, because this is a perfect square trinomial. It's x squared minus 1 quantity squared. So if I divide it by x squared minus 1, I should get x squared minus 1. What I'm getting at, if you're going to do a problem like this, I'm just going to show the setup briefly. You would take this and say that you're going to divide x squared plus 0x minus 1 into x to the fourth plus 0x cubed minus 2x squared plus 0x plus 1. Thank you, Ernie. Do you see what I've done? I've left space holders for the missing exponents in the divisor and what we call the dividend, the thing underneath this division symbol. Are we okay there? Now, with the problem I've done, and that's why I was feeling a little bit unsettled when I wrote it, I know that the first part of this is x squared. And when I multiply the x squared times the x squared, I'm going to get an x to the fourth. And because I have a 0x here and multiply by x squared, I'm going to get 0x cubed. But there are times not everything goes cleanly like that. I'm just going to put etc., etc. I'm not finishing that problem. But we need to slide just enough I can see that part there, Ernie, the x to the fourth. More. There we go. Take this and rewrite it this way. Make sure you provided a column for each missing power of the variable. Each missing exponent, if you will. X to the second, I was missing an x to the first. Provide the column. I had x to the fourth, leave a space for x cubed. Then you had x squared, a space for x. I'll leave that there. We'll just leave that for the moment, Ernie, and I'm going to walk up front. Now what I want to find is a type of problem that we have done in each case and see if we have done the preparation that we should. Okay, I'm on page 266, and I just have centered here number 10. Okay, you look at that. What approach are you going to use in 10 as you just eyeball it for a moment? What would be your reaction? What two approaches could you use?
Rewrite it where everything is
You could just
divided by 6.
Okay, you could just...
Squared.
Now, what I'm going to ask you, Ernie, in camera 1, will you go to where, below the clock and to the left of it, you see a 6 into 12x squared plus 6. Do you see that part? Will you bring that up on camera 1? 2, sorry, curl, sorry. That's one approach you could use. Or, now slide over to your left a little bit, Ernie. You could have set it up right there and then drop it just enough. You could have done it that way, where you put each part of the binomial over 6. Now back to the document cam. Do you see your choices? Mm-hmm. I don't have a recommendation for you there. My own approach would be to try it two ways, to illustrate it for myself in both ways, but you're going to have to choose what works for you. Now, as I look at number 15, here you're given the trinomial and told to divide by what? 3x squared. Again, you have what? You have the choice. Maybe as you do it, do one way, do the next one the alternate way, so you get practice both ways. Then, as we go up to 267, let's see. Look, no, that's not yet. I can't get the camera head to stay about where I want. Now, let's look at number 30. 120x to the 12th, etc., divided by 12x to the 9th. something like this might be inclined the long division process. But again, it's sort of a dicey proposition. Be careful that everything is in descending orders, and I think we're okay, but look at 27. I just noticed something there. In 27, what would you be more inclined to do in 27? Rewrite that as negative 15a to the 5th plus 20a to the 4th plus 25a to the 3rd. That is, do it in descending order. Now notice the last part of that. You'd have 25a to the 3rd divided by 5a to the 4th. You're going to end up with an a to the minus 1. 5a to the minus 1. So be a little bit cautious there. That's a little bit unusual in that one. Okay, coming off there. Then there's more fun.
Hey.
Oy vey, huh? Now we come down to 55. 8k to the 4th, etc., divided by 2k minus 3. No choice here. Long division. And notice that keeps going. Same argument. Coming off there, the next level of difficulty, 66. Now this is one I was planning to do, very similar to this, but what are you going to have to do long division on 66 in this kind of problem? You'd have to write y to the 3rd plus 0y squared plus 0y minus 1 divided by y minus 1. Number 63 right above it. Rewrite 63 as r to the 4th minus, r to the 4th plus 0r to the 3rd minus 2r to the 2nd plus 0r plus 5. Be careful. Okay, coming off there. I think that's one of the worst ones. 67 is very similar to what we've done. Do you recognize the answer right out of the gate? I hope you see a squared plus 1. Well, we have a lot of problems that you're going to have fun doing. We're going to do 1 through 73 odd. 1 through 73 odd. And with that, as Ernie goes to our slide and to our music, we're listening to the Rolling Stones. And what is the choice?
Right down the
Aren't you?
page.
Rod Stewart, that's the roll.
I wish it would rain.
I wish it would rain. Okay, an optimist. There we go. Have a great day.